Hi guys, today it's Mr. Harn. We're going to do a short video and discussion on free-falling objects. To start off with, we think about what an experiment that Galileo did, and we consider that we have a falling object, just a brick, okay? So how fast do you think that brick's going to fall, and how much force do you think it's going to fall with? All right, so we got a brick that's falling on this guy. Obviously he's got a certain amount of time to get out of the way. All right, well, if we jump up a few chapters and a bit more in material, we do take Newton's second law and we realize that force is equal to mass times acceleration. So, the more force there is, the more acceleration is. So, when an object is falling, there's a relationship between mass, acceleration, and force. So, now, we got one brick falling. Let's take into consideration, what if we drop two bricks on this guy? Is it going to fall faster? Is it going to hit him with less amount of time? So based on our discussion a second ago, and we should know that all objects are going to fall at the same rate independent of their mass. So it's going to fall with the same rate. He has the same amount of time to get out of the way of two blocks that he did to get out of the way of one block. Okay, so let's look here at this picture analogy. We have an elephant which has a much greater mass, so he would represent like the two bricks. Well, he's got a much greater mass, so he's going to hit with a much greater force, but the ratio of mass to force is the acceleration, and it's still the same as we see over here on this side with the little character. So this character only has a mass of 1 gram. He's going to hit with less force, so the ratio of his force to mass is still 10 meters per second as his acceleration. So you have the same ratio of acceleration. So note, he doesn't fall faster, he falls with more force, not with more acceleration, not with more speed. So if two objects have the same acceleration, then they would travel the same distance in the same time. Now, this one that has 4 blocks on it is going to hit you with more force than this one that has 1 block. Okay? But it takes the same amount of time, and they travel the same distance, and they hit you traveling the same velocity with that. Okay? So don't confuse hitting harder with hitting you in a shorter amount of time or falling faster. So we have a short clip here.
Feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that?
So we're going to watch just a small clip of an experiment done on Earth where they remove the air from this big chamber.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air.
4. 1, 2, 1, release.
Exactly the same. Feathers don't move, nothing. That's just...
So you can see here that when the objects are, when there is no air around that object, then those objects fall exactly the same. But you still should notice that which one hit the ground harder. The bowling ball hit harder, but it took the same amount of time as it did the feathers. So remember, don't confuse hitting harder with a shorter amount of time or actually falling faster. So the next question here, well then, how fast does it fall? What is this acceleration that we're talking about? And of course, it is the acceleration due to gravity. And on Earth, it's at 9.8 meters per second squared, okay? And that does vary based on the distance away from Earth and universal gravitational law. For now, we're just talking about the acceleration due to gravity close to the surface of Earth, 9.8 meters per second squared, or 32 feet per second squared. So, or another way to refer to this constant is 21.8 miles per hour per second. So if we take a moment and write that out, we're just going to round that to 22 miles per hour per second. So, if we go down here and we answer our little question here, what does it mean? Excuse me. What does it mean for you to be falling for 1 second? Well, if you fall for 1 second, you'll go from 0 meters per second to 9.8 meters per second. Okay? So 9.8 meters per second probably doesn't make a lot of sense to our brain. It also means you'll go from 0 to 32 feet per second, which is probably a little bit more because now you're talking about going 32 feet in a second. But I think the better understanding of what happens is over here. If you're accelerating at 22 miles per hour per second, if you fall for 1 second, you'll hit the ground traveling 22 miles per hour. It's pretty fast. Does this ever stop? Does it just keep getting faster and faster, or does it stop? Well, obviously, with air resistance, they do not just keep getting faster and faster. They do reach a maximum velocity. It's called the terminal velocity. That's the maximum velocity of an object is reached when the forces are balanced. So what we see is when an object is just released, the amount of air resistance is very small. As that object speeds up due to its acceleration, the amount of force or air resistance increases. And there eventually becomes a time when the air resistance or drag is equal to the weight, the object falling, and then it reaches terminal velocity. It continues to fall, it just doesn't fall any faster. Okay? So we can look quickly at this graph of an acceleration due to free fall of someone who's jumping out of an airplane, a parachute. So if you jump out, what happens when you jump out of the airplane? Your velocity increases. So you start off down here at, say, you have 0 velocity. Sometime later, you're at 20 velocity, whatever it is. All right, your velocity is increasing. But notice what the curve is doing. The rate at which you increase is decreasing. So down here, you're accelerating due to gravity, and that's equal to 9.8 meters per second squared. Up here, the acceleration is 0. You have no longer increasing your speed. You're still falling, you're just not getting any faster. Now when we open the parachute, what happens to your velocity? Your velocity actually starts to decrease. But then the rate at which it decreases eventually reaches 0, and we're back at terminal velocity again. So I like to look at this in this terms. This is, you're getting faster and 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 faster until you travel a certain speed, and that speed stays the same. Now you open your parachute, you get slower and slower and slower and slower and slower and slower and slower until you slow down to a constant speed again. So the rate at which you speed up or the rate at which you slow down changes. Okay? So if there's a pattern, then we can mathematically solve that pattern. And so what we're going to do is let's consider 10 meters per second per second. So we're just going to use to one significant figure for fast calculations. So if the time an object falls, okay, if we just use this time here, 1 second, then the velocity is getting 10 meters per second every second. So it was at 0, so the initial velocity is 0. So it's now 10 meters per second. If it travels for 2 seconds, it will now be at 20 meters per second. 3 seconds, each time it's getting 10 meters per second faster, it's now at 30 meters per second. 4 seconds, 50 meters per second. Excuse me, got a little ahead of myself there. 30 meters per second. 40 meters per second. And then 5 seconds would be 50 meters per second, because every time it gets faster by 10. So this is a pattern we use. What about the distance? The distance also follows a pattern. And remember, the beauty of this, or the point is, all objects follow this pattern, assuming there's no air resistance. And so we can use that pattern to begin studying the motion of objects falling. So the formula that we use to determine the distance is the distance an object falls is dependent on its initial velocity times the time it travels at, plus 1/2 the gravitational acceleration times the time squared. Now the initial velocity is 0, so we can remove that portion. So the distance an object falls is 1/2 gravity, we're using 10, 1 second squared. If you do this math, you get 5 meters. Now we can continue to use this formula for 2 seconds, and we get 20 meters. All right? Now I'm not going to show the math on each one. I'm just going to put these answers up here because I want you to memorize this pattern. And the pattern is 5, 20, 45, 80, and 125. So we want to use that pattern to solve some problems conceptually. So the distance an object falls is 5, 20, 45, 80, and 125. So 5, 20, 45, 80, and 125.